Okay, so as we end this lecture series with this third video, we'll discuss periodic trends. And I think one of the most important periodic trends is the atomic number, of course. We've already taught you that the atomic number tells you the number of protons, and that also gives you the identity of the atom. But interestingly enough, back in Mendeleev's time, the guy who actually organized the periodic table for the very first time, he organized it using just the atomic masses, right? Which is not the atomic number, or not the number of protons. Interestingly enough, right? But somehow he was still able, using his methods, able to organize the periodic table in such a way that he left gaps for future elements to be discovered, which in the future were actually discovered. Which also makes it even more crazy because the nuclear atom, right, wasn't even discovered until 35 years after that, right? So he didn't even know protons existed. And then it wasn't even until Henry Moseley that used the concept of the atomic number experimentally to kind of relate it to the number of protons, right? And the number of protons is the identity of the atom, and so the basis of all periodicity, right, or atomic trends, is based on the atomic number. Okay, so the very first, not the very first, but sorry about that. Make sure I'm still on a pen here. Yeah. So so what is periodicity? Well, periodicity is basically a pattern, right, that exists among the periodic table from left to right, right to left, or bottom to top, or top to bottom, that explains some chemical properties, right? And so one of them could be the size of the atom or ions, could be ionization energy, could be electron affinity, and other chemical trends, right? So the first one is atomic size. So what exactly is atomic size? Well, there's two types of atomic size. There is the atomic radius that's non-bonding, also known as the van der Waals radius. That is the distance between the nucleus and the outer edge of the electron cloud, or where the electron distribution is, right? Which is kind of like I guess the most intuitive definition then of atomic radius, right, for the non-bonding atomic radius. But the bonding atomic radius, right, is actually when you have a covalent bond between two atoms, it's actually half the distance between the two nuclei. And that gives you the bonding atomic nucleus, right? So both of these things are important, right? Both of those things are important. So what is the trend with product the atomic size or the atomic radius? Well, radius increases as you go from right to left, and it goes, and as the radius also increases as you go from top to bottom. And so elements over here on this side of the periodic table, the bottom left, are the largest. Right? They're the largest. And so there's also atoms that are on this side right here, which is the top right, those tend to be the smallest. Right? Those tends to be the smallest, right? And so the bonding atomic radius, though, right? The bonding atomic radius, though, so this was just the regular atomic radius, but the bonding atomic radius actually tends to decrease from left to right, right? And so, interesting enough, so that's from left right here, right, to right, right? The bonding atomic radius actually decreases from left to right, and so across the period, right? And that's because of a larger effective nuclear charge as we go across from left to right. And so when two nucleus gets together, right, the covalent they interact with each other, and so it actually decreases from left to right. But then also the atomic bonding radius tends to increase from top to bottom, right? From top to bottom, just like the atomic radii itself, because of the number of electrons increases as you go down the periodic table, right? From one group to one period to the next, right? Go down a group, the number of electrons increase. So the bonding atomic radius actually increases going down because of the increased number of electrons. That N there stands for electrons, like number of electrons. And then this ZEF here is the effective nuclear charge. I'm pretty sure. Effective nuclear charge. All right, so these things have an effect on the atomic radii, whether bonding or non-bonding. Okay. So let's take a look at the shape of the size of ions. Let me close my face here so that you can't see, so you can see the whole thing, right? Uh, so this is a lot like atomic radius, right? And it depends on what's like around, but it's determined by the interatomic distances in ionic compounds, right? And so the ionic size depends on the nuclear charge, which is that ZEF thing we talked about a second ago, and then the also depends on the number of electrons, and then also depends on what orbitals each electrons reside in. So, and I don't know why, but my dog is barking at something, so I'm sorry about that. Anyway, so if you take a look at it, right, this is group 1A, the ions of group 1A, lithium here, no sodium, potassium, rubidium. And as you can see, as you go down the periodic table in one group, the it gets larger, right? And the same is true here too. When it gets larger, right? For for a neutral atom, okay, which we had already discussed that. We already discussed that in the previous slide, right? But it's a kind of a different little pattern here for cations and anions, right? So cations still kind of follow the same pattern, right? These the orange ones here are the cations, right? So you can see that the cations are still pretty big here and pretty small there, right? But it's actually completely different for the anions. Look at the anions. The anions actually look pretty similar. Their size are pretty similar. They get bigger as they go down, but they tend to look the same size, right? So I guess the point of this is to show you that it's not just a I mean, this is pretty close to each other. Look at that right there, right? 2.07, 2.06. That's barely anything different, right? Barely anything different, right? And so they seem to be very, very similar to each other, right? They get a little more different as you go up here, but as you get down here to the bottom of the periodic table, there's a very small size difference between the anions, and so it's kind of interesting, right? And that is because actually, by the way, remember we said in the previous slide, it's because the number of electrons increases, right? Sorry, the number of electrons increases right here. So as you go down a group, okay. And so here's some reasons why that we see these trends. Cations are smaller than their parent atoms, right? Well, that makes sense because they have one less electron, right? The outermost electron is removed, and repulsions between the electrons are reduced, so they're much smaller. So we'll take, for example, rubidium here, which is 2.3 angstroms. 2.2 angstroms, and then rubidium's ion is 1.66 angstroms, right? Much smaller. And that makes sense, again, because you've lost an electron, and so there's less repulsion, so it's much smaller. And the thing I mentioned in the last slide was this right here. Anions are much larger. They're very large, right? And than their parent atoms, and they're basically the same size because they're all just extra electrons, but they're much larger because they're actually gaining electrons, right? And the added electrons will increase repulsions, and so the electrons make the radius bigger, and so it's a little bit more complicated with ions. Okay, a little bit more complicated with ions. And so the size of atoms. Okay, so what is the isoelectronic series? In an isoelectronic series, ions have the same number of electrons, and so the ionic size decreases with increasing nuclear charge, right? So say you have an isoelectronic series of 10 electrons right here, right? And here's the example right here. There are 10 electrons right there for oxygen, but it has 8 protons. Okay, and then so the 10 electrons isoelectronic with it's isoelectronic with neon, right? Because neon is the noble gas, right? That has 2 electrons in the first shell and then 8 electrons in the outer shell, so it's a noble gas, right? And so atoms that are around neon want to either lose electrons, remember, or gain electrons so they can have the same number of electrons as neon does. And that would give them a full outer shell. And so these atoms here, right, that have 10 electrons, right, they're isoelectronic with neon. Isoelectronic with neon, right? And so when when oxygen gains two extra electrons, right? So that can be the same as neon, right? It's got an atomic radius of 1.26. Fluorine, right, gains just one electron for a full shell to 10 electrons, and it's a smaller radius, right? And then sodium here gets even smaller because it loses an electron. Magnesium loses two electrons, right, and so on. And so, as a as the nuclear charge increases, right, with an isoelectronic series, right, the ionic radius decreases. And again, that is because you as you gain more electrons, right, you get bigger because of repulsions. But as you lose electrons, right, uh, you get smaller. And so, fluorine and oxygen over here are bigger because they're getting electrons, right? They're stealing them from the metals, whereas the metals here are losing electrons, right? And so here's aluminum here, lost three electrons, so it's the smallest, right? So decreasing ionic radius as you, you know, in an isoelectronic series, right? As you lose electrons, right? So what is ionization energy then? Well, ionization energy is actually the minimum amount of energy required for removing an electron from any given atom, right? So there's two different ones, right? Well, they're not different; they're just in order, right? The first ionization energy is the amount of energy required to remove the first electron, and the second ionization energy is the amount of energy required to remove the second electron, right? And so you can imagine then that things that are in group one, right, uh, are they have very low ionization energies, right? Like here, sodium right there, right? These are all metals right here, right? Sodium. The next one over is magnesium, right? So that's group two, right? And they all have very low ionization energies because they are all ready to give up electrons. Aluminum too, low ionization energy because they're ready to give up electrons to get to their full shells, right? To get to their isoelectronic state, and be like neon, right? But then you go over here to things like the noble gases, right? Man, the noble gases ionization energy right there is like 11,999. That's because the noble gas doesn't want to lose any electrons, so it's going to take a lot of energy for you to remove an electron from a noble gas, right? Chlorine too, right? Remember, chlorine steals an electron from a kitten. It's got a really high ionization energy too because it doesn't want to lose an electron because it's only one away from a full shell already, right? So the thing to know about this is that ionization energy is ionization energy is always highest with the metals because they want to lose electrons, and then ionization energy is always very high with the nonmetals because they're trying to gain electrons because they're so close to uh, being full shells already, right? And so this is this is the trend that we have. The first ionization energy actually tends to increase across the period. So this is the periodic table right here, right? Sorry, that's really rudimentary, but as you go across the period from left to right, the ionization energy increases, which makes sense because you're trying to as you go towards the right, you're trying to gain electrons, not lose electrons, and on the left side, you're trying to lose electrons. Excuse me, lose electrons. So generally, the ionization energy will increase across the period, and then the first ionization energy will actually decrease as it goes down a group, right? So as it goes down, it decreases, and that kind of makes sense too because there's a lot of electrons once you get down there, right? When you get to the bottom of the periodic table, there's a lot of electrons, so it's not so important anymore, and so they'd rather just keep what they have, right? So that's the trend that we have there for the first ionization energy, right? So what are some of the factors that influence ionization energy? Well, smaller atoms have a higher uh, 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 smaller atoms smaller atoms have a higher ionization values, right? So, uh, but this chart actually is actually really cool because if you see this right here, right, they So, what are the trends with first ionization energy? Well, as we already said a second ago, the first ionization energy generally increases across a period, right? So, if I draw you a little rudimentary periodic table right here, right? As we go across the periodic table, the ionization energy increases, right? And the reason why that is because things on the right hand side are nonmetals and they want to gain electrons, right? And they don't want to lose electrons, so their ionization energies are really high, so they don't lose those electrons, right? Whereas things over here, like the metals, right? Like the group one, group two, they're ready and willing to lose those electrons to get down to their full electron shells, and so they have very low ionization energy, so they can just readily get rid of those electrons, right? And then the first ionization energy generally decreases as you go down a group. So that means as you go down a group, right? So let's go down a group like that, right? It decreases, which means that smaller atoms, right, will have uh, smaller atoms will have uh, a lower ionization energy, right? Um, and so when you get down to here, right, the 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 ionization. Oh my God, what am I saying? Let me try it again. Oopsie. So, what are the trends when it comes to first ionization energy? Well, the first one is that the first ionization energy decreases across a period, right? And so, if I were to draw you a rudimentary periodic table right here, as we go across the periodic table, the ionization energy increases, right? And we talked about this before because things on the right hand side of the periodic table are they're not very, but they are nonmetals, and they want to gain electrons because they're so close. They only have one away or two away from getting a full octet, and so they rather gain electrons. They're not going to want to lose any electrons, and so it takes a lot of energy to remove an electron from them. Whereas metals on this side of the periodic table right here, right, they're readily available to lose electrons, and so their ionization energies are very low. So they can just get lost. They can just lose their electrons to get to their octets or their full shells. And then the second one is the first ionization energy decreases as you go down a group. So as you go down the group, the first ionization energy decreases, right? The S block and P block elements show a larger range of ionization energies, right? The D block generally increases slowly across the periodic table, and then the F block elements show only small variations, right? So this a very so even though we have this trend, they're very slow trends, right? And so, uh, but there's definitely a huge difference in the first ionization energy of the alkali metals and the alkali earth metals, or the also known as group one, group two, versus all the nonmetals, right? Versus the nonmetals, and so smaller atoms have higher ionization energy values, right? And so So, what are some factors that influence the ionization energy? Well, smaller atoms have higher ionization energy values, right? And then ionization values depend on the effective nuclear charge and the average distance of an electron from the nucleus, right? From the nucleus, right? So, you look at this little chart here, right? Just as we said before, as you go from left to right, the ionization energy increases, and um, uh, as you go from bottom to top, the ionization energy also increases, right? And so things like fluorine and chlorine and neon, of course, all those guys, they rather not give up an electron, so they have very high ionization energies, right? Very high ionization energies. So there are some irregularities in the trend, though, and so one of these is that if you look at an electron, an added valence electron, like on the next element, the trend kind of like falls apart, which is interesting. And so the example here is that nitrogen, right, has these three electrons that are in its three orbitals, right, and so it follows the trend of the more far up and to the right you get, right, the higher the ionization energy. But oxygen, though, because it has one extra electron right here in this next p in the first p orbital right here, right, it actually doesn't follow the trend, so it actually has a slightly lower energy, even though it's to the right, right? You would think that because it's the trend is, you know, from from left to right, higher ionization energy to the top, right? But and nitrogen is actually, on the periodic table, nitrogen is here, and then oxygen is right next to it, and so you would expect that oxygen would have the higher energy, higher ionization energy than nitrogen does, but in fact, nitrogen uh, has the higher one, right? Because of this one extra little electron that oxygen has, which is interesting, right? So if you go back to this slide right here, you can see that nitrogen right here has a higher ionization energy than oxygen does, right? So, cations, what about them? The electrons are lost from the highest energy value level, right? So the n equals the highest number they have, which is basically where their valence shell is, right? That's where they lose their electron from. And so for lithium, it loses one of the 1s. So for lithium, it's a 1s2, right? Lithium plus ion, it's a 1s2, and it's because it lost the 2s1 electron it had, right, to some kind of nonmetal, okay? Because its original electron configuration was 1s2, 2s1, remember? Right? And so it lost a 2s electron, right? Oh, I lost my s right there. There it goes, right? Iron, right here, right? Iron right there. It's iron plus one, right? That's iron plus one. And so there is this electron configuration there. It lost two 4s electrons, right? Because that's the highest number. And so it's not necessarily the highest like orbital, which is d, but it's the highest number, right? And for iron, it's the 4s, the two 4s electrons, right? The two 4s electrons, which are actually, they fit right between here and here, right? So it used to say 4s2 right there, but those are the two that iron lost, right? Those are the two that iron lost. It's gone to some nonmetal, right? And so now that's iron 1 plus, and so that's its new electron configuration. So the important thing to note here is this: it's that you lose electrons from the highest energy level or the highest n value, right? It's not necessarily the highest orbital, like SPDF orbital, right? It's the highest n value that you lose your electron from. And since the highest one for iron here, right, was the 4s, it lost it from there rather than losing it from the 3d6 orbitals, right? Anions, on the other hand, they tend to gain, right? And so they'll gain it right in their, right there in their valence shell, right? So for fluorine right there, before fluorine got the electron, that used to say 2p5, right? So it gained one electron in its 2p orbital, right? And so anions are always, they try to get this last configuration right here, right? This kind of general configuration, where n is the nuclear, sorry, n is the principal quantum number or the energy level, and then s, p2, and p6, right? So as long as it has s2 and then p6 in there, and these are the energy levels, that anion's happy. That anion's happy. So what is electron affinity? Well, electron affinity is the energy change accompanying an addition of an electron to a gaseous atom. And so here we have chlorine, which was a gaseous atom, right? And so it gained an electron, became Cl minus, right? Which is actually an ion that you can actually dissolve in water, like sodium chloride, right? And so this is typically a very exothermic reaction. For most elements, it's a negative. It's negative, right? So it's a very exothermic reaction, meaning that it produces a lot of heat. Right? produces a lot of heat. So electron affinity. So another way of saying electron affinity is is uh, is how much another atom likes electrons, right? It's affinity for electrons. And so when you look at the trend of electron affinity, right, um, the there's not much change within groups, right? Right, but across a period, electron affinity generally increases, right? Which makes sense, right? So the more negative you are right here, the more you want electrons, right? And so as you see here, of course, the halogens here like fluorine and and chlorine and stuff, right? And bromine, they have very high electron affinities. They really want that affinity, okay? And so there's definitely exceptions though. You would think as again, metals don't have an electron affinity. Sorry, non-metals. Yeah, metals don't have an electron affinity because they want to give up that electron. So that means that non-metals then want electrons, so they have a higher electron affinity. So you would think then that the general rule is across the period or across the periodic table from left to right, you would have more electron affinity on the right hand side and less electron affinity on the right hand. You would have more electron affinity on the right hand side and less electron affinity on the left hand side. And that's generally true except for three exceptions. These are the three here. Group 2A, right? Somehow right here, uh, it went down electron affinity. But why is that? Well, it's because the S sublevel is full. That's why. That's why, right? The S sublevel is full for those guys, and that's why it kind of just screwed up our general pattern, right? What about group 5A? So here's group 5A. Oh my God! Again, kind of just dropped there, like especially with nitrogen and phosphorus right there. Well, why is that? It's because they have a sublevel that's half full, right? And then group 8A, of course, which is the noble gases. They don't need electrons, right? They have a full sublevel of p orbital sublevels. So why have an affinity for electrons when you don't need them anymore? You have your 8 electrons, you're happy, right? And that actually ends the lecture. And so by this time now, after listening to this 2 hour or more lecture, you should be able to define waves in electromagnetic radiation. You should be able to define what a quanta and the photoelectric effect is. You also be able to describe atomic emissions, spectra, and the Bohr model. Also describe the Heisenberg uncertainty principle and its implications on quantum mechanics. You should also be able to define the quantum numbers, which are n, l, m sub l, and m sub s. You should be able to define and describe the s, p, d, f orbitals, right? And also define what the Pauli exclusion and the Hund's rule are. Pauli exclusion principle and the Hund's rule, right? Electron configurations and orbital diagrams, and then also describe and explain observed periodic trends. All right. And that's it. That's going to be what's going to be on your test. And so I'm actually working on your review sheet right now, but by the time you watch this video, it'll already be posted. And so good luck, and I will see you for the exam on Wednesday.